Hi everyone, my name is Peter, and this summer Anik and I researched optimal pedaling of foster trees. Alright, so first, the outline. So we're gonna go over some relevant definitions of grass and grass pedaling, and then we'll go over the optimal pedaling number of maximal foster trees, and then we'll finish up with some future work. So first, the definition of a graph. So a graph is an ordered pair, V, E, in which V is a set of vertices and E is a set of edges. And so in this graph right here, the blue circles are the vertices and the lines connecting them are the edges. And then two vertices are adjacent if there's an edge between them. So all of these circles are adjacent to each other because they all have a line connecting each other. And then the degree of a vertex is the number of edges at that vertex. So each blue circle has a degree of 2 because there are 2 lines coming out of each circle. And then some applications of graphs. So the first application is the internet. And on the internet, the vertices are devices, routers, and web pages. And then the edges are like wires that connect them or packets that are sent between them. Social networks is another example. So Facebook and Instagram. And on Facebook and Instagram, people and accounts are the vertices. And then if you follow each other or are friends with each other, that's an edge. And then also country maps, like the map of the US, are graphs. So the cities would be the vertices, and then the roads and highways that connect the cities are edges.
Hi, I'm Monica. So to begin to understand what lobster trees are, we first have to understand the simplest version of a lobster tree, which is a path. So a path is just, to use Peter's definition, is just a bunch of vertices and edges connected. For example, this path you can see up on there is just a path that is like 5, which just means it has 5 vertices with edges connecting it. And then an expanded version of a path is a tree, which is a graph in which any 2 vertices are connected by exactly 1 path without repeat edges. A leaf is a vertex that is adjacent to exactly 1 other vertex. So in this diagram, the vertices 1, 2, 3, and 6 are all examples of leaves, while the 5th vertex is an example of a degree 2 vertex. So our main focus here was a lobster tree, and lobster trees are trees in which every vertex is within a distance 2 of the central path or body. And on this diagram right here, this main path is what we call the body for all of our work. And then the 2 vertex subpaths not on the body are lobster legs. This right here is a lobster leg. And each vertex on the central path adjacent to a lobster leg is a joint. And then the joints are right here. And each vertex adjacent to a joint and at least 1 leaf is an elbow. And then, so on the left, we have what we call a maximal lobster tree, which is a lobster tree in which there are n vertices in the body and each joint is adjacent to at least 2 lobster legs. And on the right, we have another example of a lobster tree, which we have unfortunately not been able to optimally pebble. So pebbling, as written by Herbert, is, or how to pebble is if we place pebbles on the vertices of G, then a pebbling move is taking 2 pebbles off 1 vertex and placing 1 on an adjacent vertex. So what this just means, in this diagram here, we have 2 pebbles placed on the 3rd vertex. So you can move 1 pebble to the 4th vertex, or move 1 pebble to the 2nd vertex. When you're moving pebbles, you can reset once you move to one side. It's important to note that it's either or. You can't move 1 pebble to the 4th and 1 pebble to the 2nd. And then another definition is a distribution of pebbles on a graph G is M solvable if for each vertex V of G, we can get at least M pebbles to V via a sequence of pebbling moves. So in this example, this graph is not 1 solvable, but certain vertexes are 1 reachable. So vertices 1 and 5 are not 1 reachable because two pebbles can only move once. So in one direction only once, meaning vertices 2, 3, and 4 are all one reachable, but vertices 1 and 5 aren't.
Alright, so the work that we did was mainly focusing on the optimal pebbling of graphs. So the optimal pebbling number, which is called pi star, is just the lowest amount of pebbles that we need, so that each vertex can get m pebbles at one point. The vertices don't have to have the pebbles at the same time. After you move the pebbles, you could reset the distribution and then move the pebbles like in a different direction. And so an example of optimal pebbling is the one pebbling of a path. The formula, okay, so for one pebbling of a path, we want to find a configuration that uses the least amount of pebbles as possible, but each vertex along the path could still get one pebble at one time. So the formula that we found is the ceiling of 2/3 n. And the ceiling function is just a round up. So if it's a non-integer, then you just round up. And so we can see an example of pebbling a path down here. So this path is length 6, and the optimal number is 4. And so you can see how it would work by placing 2 pebbles on the second vertex and 2 pebbles on the 5th vertex, and they each can pass a pebble to the neighbor. So each vertex on this path could get one pebble at one time. And we know it's the optimal number because there's no way to do it in 3 pebbles. You have to use 4 pebbles. And so the formula of ceiling 2/3 n, we got that because when you have a path, you could split it into chunks of 3, and each chunk of 3 would need 2 pebbles. So you get 2/3. But then the ceiling function is there because if the path doesn't divide evenly, you'll have a remaining vertices outside, and each of those remaining vertices needs their own pebble.
So in this diagram, we have an example of a length 7 maximal lobster tree. And as you can follow the chart, it starts out in its most original form with 3 lobster leg joints. But then over here, we have the exact same path, just reorganized. So you can see that each joint has 2 lobster legs as opposed to only the middle one having 2 lobster legs. And each lobster joint we denoted as vertices 1 all the way to n-4. The n-4 being because we can ignore the first 2 and last 2 vertices. And so the theorem we created was that for the optimal one pebbling of a lobster tree length n, the optimal way to pebble it is the floor of 3/2 n-4 plus 3, and a floor function is just an example of division in which you round down to the nearest integer. So to prove that this equation was right, we first had to prove that this was the upper bound of pebbling a lobster tree. So that just means we can do it in this amount of pebbles and we don't need any more for that. So on the left, we have an odd, you can't see it almost, but we have odd maximal lobster tree. So in this algorithm we created, for the first and last lobster joint, you would place 2 pebbles and then you have an alternating pattern of 3 and 0s to ensure everything is 4 reachable. And 4 reachable just means that you can move pebbles to 2 distances away, and that ensures every leaf gets at least 1 pebble. And on the right, we have an example of an even length lobster tree. And again, following our algorithm, we would place 4 pebbles on the first lobster joint, and then an alternating pattern of 0s and 3s, and 2 pebbles on the last lobster joint. And then this diagram is an example of how we can get at least 4 pebbles to every joint. So there are 2 ways you can pebble. You can move left to right and right to left in this example. So at first we move 1 pebble from B1 to B2 to ensure that one gets 4. And as it passes, it keeps passing more and more. And that middle vertex, that when we get 0, it would get 2 more if you were to be going from right to left. And then another way in which you can path a maximal lobster tree is you can have everything meet at one vertex. So in this even path, we have things moving left to right to meet at the second vertex, and things moving right to left to once again meet at that second vertex.
Onto the lower bound. So another study before us found that for optimal distributions, the leaves in a distribution, so right here and right here, would never have any petals on it. And the elbows, so right here and right here, would have at most 2. However, we weren't really satisfied with that. And so we wanted to prove why you would never need to place pebbles on any of the legs. And so the first step to doing that was proving why it wasn't optimal to have 2 pebbles on an elbow. And so the way we did this was by going case by case. So if there are 2 pebbles on an elbow, there's 2 possibilities. And the first possibility is that there's 2 pebbles on both elbows. And so in this case, you could just take 1 pebble from each elbow and move it into the middle joint. So that middle joint would have 2 pebbles, which could then pass 1 up to the elbow, giving that elbow 2, which could then pass 1 to the leaf. And so in this way, between these 2 graphs, we see we use the same amount of pebbles, but we didn't have 2 pebbles on any elbow. And so we did that same process down here. And so we were able to prove that you don't need 2 pebbles on an elbow, you need less than 1 or 0. And so after that, we moved on to going from 1 pebble to 0 pebbles. So we did the same steps that we did in the previous slide, proved why it was the exact same to just take off pebbles from the elbows, move them to the joints. And so by doing that, we were able to prove that we could only focus on putting pebbles along the main path and not really worry about the legs. So by doing that, we're able to collapse the lobster and make it only a path. And that path, that number could act as a lower bound for the whole fully expanded lobster. And so after we did that, we started focusing on pebbling a path. And not just placing 1 pebble on each part of the path, but each vertex in the path has to get 4 pebbles, so that way when it's fully expanded, each leaf could get a pebble. And so the way that we approached this was by seeing how many more pebbles we would need if you increase the length of the path by 1. And so what we found is that when you increase the length of the path by 1, sometimes you need 1 more pebble, as seen in the first example, but sometimes you need 2 pebbles more for each increase, and that's seen in the second example. But what we found is that after you increase it by 1 and you need 1 more pebble, the next time you increase the length by 1, you'll need 2 more pebbles. So for every time you increase length by 2 vertices, you'll need 3 more pebbles. And so that's how we got this formula down here. 3 has K, where K is the length, because every increase of length 2 is just 3 more pebbles. So the formula that we got for the lower bound is the floor of 3 has n minus 4 plus 3. And this formula for the lower bound is the same formula that Annika talked about for the upper bound. And so since our lower bound and our upper bound were exactly the same, we know that the true formula for the maximal lobster is this right here.
Okay, so sadly, we didn't have enough time to complete everything we could have wanted, but if we had had more time, here's a few directions in which our project could have gone. So the first way is we could have determined the optimal non-pebbling number of non-maximal lobster trees. So we gave an example of a non-maximal lobster tree, but it's just not 2 or more lobster legs at every joint. And then we could have also determined the optimal pebbling number of a path for which some vertices are 2 reachable and others are 4 reachable. And this just means taking away, again taking away a leg or making a leg that is only distance 1 from the path. Thank you. Are there any questions? Yeah. Is there a real world application?
Yeah, like social networks, and what I like to think about is like Amazon delivery. So sometimes maybe there's like a refuel station, you can like optimally place those stations so that the trucks get hit every part. Something like that.
Is that all? Okay, great.
Quick reflection on what your favorite part or what surprised you about the whole experience.
I had never done math research and I sort of just interpreted math was as much as calculus, like there's always a clear cut answer. But this definitely was not that. And I really enjoyed making progress and even not making progress when we thought we did. And I liked the trial and error of it all.
Yeah. At first I thought the math was really easy, it was just placing rocks on a graph, but I didn't realize how like complicated it was. And I really experienced the math process where you kind of think you got it right, and then you try and prove it and you find out it's wrong. So it was a lot of.
We also like to thank Matthew Gherman for all of his mentorship. Thank you.